We're going to review Chapter 6 by looking at some old test problems. Here's some true-false questions. True or false, the Gauss-Seidel iterative method is generally slower than Jacobi. That's false, it's generally faster. Jacobi iterative method converges only if the matrix is diagonal dominant. That's false, it converges if it's diagonal dominant, but not only if. Gauss elimination, when applied to a general n by n linear system, requires order n cubed arithmetic operations. That's true. It's 1/3 n cubed multiplications. Then right below here is a problem where you're supposed to write out the Jacobi and Gauss-Seidel iterations. Just solve the first equation for x, second equation for y, third equation for z. And that's the Jacobi method. And Gauss-Seidel is the same, except that you use xn plus 1 in the second equation because you have a new value. You have a new value of x and y, so you use them. So the circle here is the only difference. And it asks if Jacobi method will converge. And well, normally you'd look and see, is this diagonal dominant? It's not, but that doesn't necessarily mean it doesn't converge. And in fact, it does converge. Here's this is the M matrix, what's called M in your text. The eigenvalues of this matrix, if the norm is less than 1, it's guaranteed to converge, but it's not, because that's not quite diagonal dominant. It's almost. But the thing is, I'm not sure how you were supposed to find the eigenvalues. That's kind of a lot of work to find the eigenvalues of a 3x3 matrix, but in any case, somehow or other, you're supposed to find the eigenvalues, and they're all less than 1, therefore it does converge even though it's not quite diagonal dominant. And here's another problem where you're supposed to write out the Jacobi and Gauss-Seidel methods, and it says true or false, the Jacobi iterative method will converge for any starting vector. Yes, because the matrix is diagonal dominant. 7 is bigger than 2 plus 1, 3 is bigger than 2, 5 is bigger than 1 plus 3. So actually they're both guaranteed to converge. Part D is over section 6.5, which we're skipping, so it wouldn't be relevant to you, but let me say a few words about 6.5 since we skipped it. This is about round-off error. When you use Gauss elimination to solve a linear system, the only error you have is round-off error, and but it can be very severe if the matrix is very ill-conditioned. That is, if it's nearly singular. You know, if it's non-singular, there'll be a unique solution, but if it's nearly singular, you're going to get bad round-off error, and it really doesn't matter what you do. You're almost doomed to get bad round-off error. For example, if you have a system of 2 equations, 2 unknowns, if you're that's basically intersecting 2 lines. If the 2 lines are parallel, there's no solution, or many solutions if they're the same line. If they're nearly parallel, there's a unique solution, but you can see that it would be hard to find the exact solution accurately if the lines are nearly parallel, no matter what you do, because just changing any of the coefficients of either a line a slight bit, it's sort of the scissor effect that'll change the exact solution a whole lot, so there's no hope of finding, no matter what you do, of finding the original solution accurately. So basically, if the matrix is ill-conditioned, that means nearly singular. There's not much you can do to avoid round-off error, but so section 6.5 is basically just about measuring how badly conditioned a matrix is. That's what this problem is. It gives you a measure of how ill-conditioned it is, so at least you'll have a warning if it's high ill-conditioned. Well, here's a problem where you're simply supposed to find the inverse of this matrix 4 by 4. Is a lot of work to find the inverse, but there's already mostly zeros and ones, so this one's not actually too much work. So you just do it by hand. This is more of a matrix algebra problem than numerical analysis, but it's in there. And here's a problem. It says how many multiplications are done by the section of MATLAB code below, which does back substitution in solving the n by n linear system. Well, you've got a double nested do loop. I goes from n minus 1 to 1, goes down, and j goes from I plus 1 to n. If that were 1 to n, it would be n square multiplications. It would execute this n square times. It's 1/2 n square because on the average j goes from half of n to n. See, I goes linearly from 1 to n minus 1, and I plus 1 is on the average half of n, so this is basically goes through this, executes this 1/2 n square times, which is a whole lot less than the forward elimination, which is 1/3 n cubed. So the back substitution is a negligible amount of work compared to the forward elimination. And finally, a couple of short answer questions. Gauss elimination applied to an n by n linear system requires approximately how many multiplications? That's 1/3 n cubed. We derived that in one of the videos and in class. The strategy of switching rows during Gauss elimination to always bring the largest in absolute value potential pivot to the diagonal is called what? Partial pivoting.